Quantum computing promises to transform technology as it is known today. From the design of new materials to the simulation of complex chemical processes, its potential is enormous. However, turning that promise into real devices requires overcoming a fundamental problem: how to protect quantum information from the noise of the environment. If you like this content, do not forget to subscribe and give it like, so you can be aware of more fascinating advances in the field of quantum computing. In this video, we will explore a recent study that marks a decisive step forward in the protection of quantum information. Among the most ambitious proposals to achieve this are the topological qubits based on the so-called Majorana zero modes. An international team has published a study in Nature that describes a new way to access the internal state of these systems without destroying their sensitive information. Majorana cubes are different from conventional cubes. While a conventional cube stores information on a localized property, a Majorana qubit distributes information in a non-local way between two ends of a designed superconductor device. This information is encoded in a property called fermion parity, which can adopt even or odd values. This feature is not associated with a particular point of the system, but with the set of both extremes, which gives them greater resistance to noise. The article highlights that topological qubits offer a path to the protection of quantum information through non-local coding. This is crucial, as a local disturbance cannot alter the full state of the qubit, which gives them a significant advantage. However, measuring a Majorana qubit presents a unique challenge. Information does not reside in one place, which means that measuring only part of the system does not provide useful information. This has been a major obstacle to research. The study addresses this problem using a simplified version of the system, known as Kitaev's minimum chain. This configuration can store information in its joint parity, which is fundamental to the functioning of the qubits. The key to progress is the quantum capacitance technique, which allows measuring the overall response of the system rather than examining an isolated part. This allows to detect the joint state of the chain and perform accurate readings in real time. Researchers also observed spontaneous changes between par and odd parity, known as parity jumps. These changes are significant, as they indicate that the system can maintain its state for a long time for logical operations. The usefulness of this advance is clear. Without a reliable reading method, Majorana qubits were more a theoretical promise than a practical tool. This work establishes an essential step for temporary control of the qubits. Although topological quantum computers are not ready for commercial use, this breakthrough removes a technical barrier that has blocked progress. This brings topological quantum computing closer to more engineering and less speculative development.